Hello and welcome to Cognito Key. You know, let's just jump right in with a question to get you thinking. So, think about this. How would you go about building a switch that's, well, smart? One that only flips on when you give it exactly the right push. I mean, it sounds a bit like something out of science fiction, doesn't it? A switch that kind of has a mind of its own. Well, believe it or not, the answer is in this really clever, four-layer device that pretty much changed electronics forever. And we're going to be talking all about this foundational component, the Shockley Diode. So, what makes this a very special switch? I mean, what's the big deal, right? What makes this diode so different from just a regular one? Come on, let's peel back the layers and find out. Okay, so your typical diode is kind of like a one-way street for current, right? The Shockley diode, well, it's more like a bouncer at a club. It's got this unique four-layer structure, a PNPN setup that acts like a switch, and it stays stubbornly off, just not letting anything through, until the voltage hits a very specific point. We call that the breakover voltage. And only then, bam, it swings the gates wide open and lets the current flow. It was invented by the brilliant William Bradford Shockley. And honestly, its genius isn't how simple it is. It's either on or it's off. That's it. This black and white binary nature is exactly what makes it such an amazing building block for all kinds of switching circuits. All right, let's get into the nitty-gritty, inside the four layers. So how does this clever little switch actually work? To really get it, we've got to look inside that unique four-layer structure. So picture this. It's basically a simple stack, like a semiconductor sandwich. You have four alternating layers, P, then N, then P, then N again. This whole PNPN setup creates three internal junctions, and trust me, that's where all the magic happens. This wasn't just about adding more layers for the sake of it, it created a completely new kind of electronic behavior. Now, trying to wrap your head around how those four layers work together, yeah, it can be a little tricky, but here's the secret sauce, the aha moment. The best way to understand it is to see it as two transistors working together, a PNP and an NPN, connected in this clever little feedback loop. And it's this two-transistor model that gives the diode its awesome latching ability, the thing that lets it snap on and then stay on. Okay, next up, the breakover point. We've seen the structure, so now let's get to the action. How does this thing actually flip the switch? Well, it all comes down to hitting that critical breakover point. The whole turn-on process is actually pretty elegant. So first, you apply a forward voltage across it. At first, nothing much happens. The diode is like a fortress with really high walls, super high resistance, and only a tiny, tiny leakage current manages to sneak through. But as you keep cranking up that voltage, you eventually hit the magic number, the breakover voltage. And at that precise moment, bam, the internal transistors suddenly trigger each other, the resistance just plummets, and current starts flowing freely. Just like that, the diode has switched on. So yeah, that breakover voltage, or VBO for short, is the key. It's that magic number. It's the minimum voltage you need to apply to flip that internal switch from being off with high resistance to being on with super low resistance. But wait, how does it stay on? I mean, does it just turn off again? Nope. That's where something called the holding current comes in. See, once the diode is on, it's latched, it's locked in. It needs a tiny minimum amount of current, we call it IH, to keep those gates open. If the current flowing through it ever drops below that holding level, poof, the diode automatically resets itself and switches right back off. Right, let's talk about a dangerous reverse. We've been talking all about turning it on, which is what it's designed for. But what happens if you hook it up backwards? Well, this is where things can get a little dicey for our little component. If you look at its VI characteristics, that's the voltage current graph, you can see this whole story laid out visually. See here. In the forward direction, the current is basically 0, 0, 0. And then it hits that breakover voltage and whoosh, it just shoots straight up. But now look at the other side, the reverse direction. If you apply voltage backwards, you get this sudden, catastrophic breakdown. This graph shows you exactly why you've got to be so careful. And this brings us to the absolute golden rule when you're working with a Shockley diode. Are you ready? It is never operated in reverse biased mode. Seriously, if you push the voltage too far backwards, you'll hit that reverse breakdown point, a flood of current will rush in, and you'll just cook the thing. It'll be permanently destroyed, it's a one-way street, and going the wrong way is a recipe for, well, a dead diode. Okay, so now that we know how it works and how not to use it, let's talk about putting the switch to work. With this super unique and precise on and off ability, where did this clever component actually get used? Let's check out some real-world applications. Really, it found its home in two key applications. First, as a trigger switch, especially for bigger, more powerful components like the SCR, or silicon-controlled rectifier. And second, in these really neat circuits called relaxation oscillators, which are just a fancy way of saying a circuit that creates a repeating, pulsing signal. So, when it's used to trigger an SCR, the Shockley diode is like a really patient security guard. Picture a capacitor in the circuit slowly charging up, just filling up with energy. The diode just sits there, watching and waiting. The very instant that capacitor's voltage hits the diode's breakover point, it snaps into action. It fires off a pulse of current that tells the much bigger SCR, okay, time to turn on. It's the perfect, precise, voltage-sensitive gatekeeper. And what about that oscillator? Well, you can use it to create a circuit that makes a rhythmic pulse, like a tiny electronic heartbeat. Here's how it works. A capacitor charges up. The voltage hits the VBO. The diode turns on, which lets the capacitor quickly discharge through it, which makes the voltage drop, which causes the diode to turn back off. And then the whole cycle starts all over again. Charge, fire, discharge, reset, over and over. But here's the thing, and this is probably the most important takeaway. You probably won't find a plain old Shockley diode in a lot of modern electronics. But its fundamental four-layer PNPN design, that idea is everywhere. It's the conceptual backbone for a whole family of power switching devices called thyristors. And these are components we use all the time today, like diacs, triacs, and even the SCRs we just talked about. So really, the Shockley diode's elegant design was a true building block for the future of power electronics. It's just a great reminder that sometimes the simplest ideas can end up having the biggest impact. And it kind of makes you wonder, doesn't it? What are the fundamental ideas being cooked up in labs today that are going to become the building blocks for the technology we'll be using tomorrow? Hey, if you found this little explainer on the Shockley diode helpful, please think about subscribing to Cognito Key. Your support honestly helps us so much in creating more content like this. And of course, don't forget to hit that like button and share this with anyone you think might find it interesting. Thanks so much for watching.